So before I move on with cardiac physiology, I'd like to revise a few terminologies that you might have learned in the past. The first one is resting membrane potential. Resting membrane potential. The resting membrane potential is the difference of concentration of ions inside the cell and outside the cell. Okay, if you recall, we studied about sodium potassium pump. So the resting membrane potential is mainly created by the sodium potassium pump. And this sodium potassium pump moves a large number of sodium ions outside. Specifically, it moves 3 sodium ions out, and at the same time, it takes in or moves into the cell 2 potassium ions. So for every 3 positive charges moved out, you're pulling in only 2 positively charged potassium ions. And eventually, this creates a difference of charges inside and outside the cell, which is called the resting membrane potential. Now, when you disturb the resting membrane potential of the cell, it causes an action potential. And anything like an external stimulus can disturb the action potential of the cell. So this picture over here shows you for the sodium potassium pump, and the pump gets initiated when the sodium ions bind to the internal side of the pump, and when sodium is taken out of the cell, it picks up only 2 potassium ions and bring them into the cell. And this happens quite a bit in the cell. So eventually, let's just say you have 1, 2, 3, 4, 5, 6 potassium ions moved in. You will have 9 sodium ions outside, right? This, for instance. So the cell is more positive on the outside than the inside, and that's how the cell gets a negative membrane potential. In case of pacemaker cells, the resting membrane potential is equal to negative 55 millivolt. Everywhere else in the myocardial cell, it is negative 90, but in pacemaker cells, it is negative 55. All right, so keep this in the back of your mind that the cell has a resting membrane potential. Okay, before we begin looking at pacemaker physiology, if you want to make a note of what action potential is, do that. Okay, an action potential is triggered when you disturb the resting membrane potential, and it causes the cell to depolarize. An action potential causes the cell to depolarize. Depolarization. So depolarization occurs when the cell's internal charge becomes less negative. In other words, it's becoming more positive. And why would this happen? It would happen because there are some positive ions entering the cell. So the inside of the cell becomes less negative or more positive. It's the same thing. Now, this other word, if you want to make a note so you don't get confused later, is repolarization. Repolarization is when the internal charge of the cell returns to a more negative value. So in other words, the cell is returning back to its resting membrane potential. Okay, so the positive charge from inside basically begin leaving the cell and start moving out, which returns the internal charge to a more negative value as it normally is during the resting membrane potential. So keep in mind one thing. the the SA nodes do not have a stable resting membrane potential. Okay, so they randomly generate action potentials and spontaneously. Okay, also keep in mind that there are a lot more positive charges on the outside of the cell than the inside of the cell. Now this graph that you're seeing over here begins at the end of repolarization. Okay, so at the end of repolarization, the resting membrane potential has returned back to a much negative value. So in case of pacemaker cells, the resting membrane potential is unstable and it fluctuates, right? So it's anywhere between negative 50 to negative 60 millivolt. And I drew a little diagram over here. I'm going to label what this diagram is so you understand as we go. So these blue channels, are sodium channels, okay? And the green channels are calcium channels. So the green channels are calcium channels. The pink channels, I don't have that color. I'm just gonna say this. Pink or purple channels are potassium channels. And then I'm going to add another channel over here. These are also sodium channels. They are just voltage gated sodium channels. Let me also label, this is the extracellular fluid, and here this is the intracellular fluid. Keep in mind, at the resting membrane potential, there is a lot more sodium and calcium ions in the extracellular fluid, and there is a lot more potassium ions in the intracellular fluid than the extracellular fluid. Okay, because the sodium and potassium ions are moved against each other by the sodium-potassium pump. It is also the inherent ability or a characteristic of a cell to want to return to its resting membrane potential. Okay, so let's begin. At the end of the repolarization is when the next action potential kicks in. Okay, so when the membrane potential is very negative, about minus 60 millivolts, the first channels that open up are called funny sodium channels. These are actually called funny sodium channels. Funny sodium channels. So these channels slowly open up and sodium ions slowly begin to leak in, because these are leaky channels. These are not sodium potassium pump. These are just leaky channels that slowly allow sodium ions to trickle in. And when sodium ions slowly trickle in, the cell starts becoming more positive. And when the threshold of the cell reaches negative 40, this opens up the second type of channel, which are the calcium channels. These calcium channels open up and more calcium ions now start moving into the cell, right? And the cell starts to begin more positive. So these voltage gated calcium channels allow a lot of calcium to pour in, and simultaneously the voltage gated sodium channels also open up. Now a lot of sodium as well pours in. The cell becomes more negative. The cell becomes more positive because you have a lot of positively charged ions moving into the cell. And the cell rapidly begins to depolarize. So right now, we are in this stage right over here. And when the cell rapidly depolarizes, the charge of the cell becomes more positive. And when the voltage reaches slightly above 0 millivolt, at this point, the potassium channels open up. When the potassium channels open up, potassium ions from inside the cell start leaving the cells, and the potassium ions move out of the cell, and the cell begins to repolarize because you have positive charges leaving out of the cell. And the cell returns back to its resting membrane potential. And as the cell begins to return to its resting membrane potential, basically prepares for the next set of action potential. Okay, so this region where you see pacemaker potential is when the cell prepares to kick in another action potential. I would also like to talk about two important types of calcium channels in here, because calcium inflow plays a major role in causing depolarization and thereby causing contraction of the heart. Okay, so there are two important calcium channels in the pacemaker cells. The first one is the T type calcium channels, and then you have the L type calcium channels. The T type calcium channels open up right over here, and they are transient channels, so they quickly open up and allow an influx of calcium ions. And then when the cell is depolarizing, you have the other type of calcium channels open up. That is the L type calcium channels open up right over here. Now the L type calcium channels are responsible for normal contraction of the myocardium. So basically, in simple terms, you can say these L-type calcium channels are responsible for how strongly the heart can contract. So when somebody has things like hypertension or some kind of cardiac arrhythmia, they can use L-type calcium blockers, which are a category of drugs that can be used to not allow the heart to contract as much. Because keep in mind, L-type causes contraction. So if you're going to use L-type calcium blockers, they're going to cause the heart to relax more, okay, and thereby reducing hypertension. Okay, these T-type calcium channels are not normally present in the adult myocardium, okay, but they are present in the pacemaking cells. So in the nodal cells and the conducting cells, you'll see a lot of T-type calcium channels because they play a very important role in kicking in the depolarization. So they open up right over here. So let's quickly see what's happening in this stage. So when the cell has just repolarized, this stage is called hyperpolarization, and the funny sodium channels open up. These funny sodium channels are leaky sodium channels. So sodium slowly flows in, cell starts to become more positive. Then when a threshold of -40 is reached, the T-type calcium channels open up, calcium ions flow in, and the cell begins to depolarize. As the cell depolarizes, the L-type calcium channels open up, and more voltage-gated sodium channels open up. The cell depolarizes. The membrane potential reaches little over 0. Other channels shut close, and the potassium channels open up. The potassium starts moving out of the cell, and the cell goes back to its resting membrane potential. Okay, and the cycle begins again. And after everything, keep in mind the resting membrane potential of the pacemaker cells is unstable. So they randomly fire an action potential when they have reached the resting membrane potential.